My background is actually from the business side. I used to teach statistics and econometrics at Stockholm School of Economics for about 10 years before I moved to the dark side and became a consultant. I work a lot with retailing in different types of retailing and different countries. With these types of projects, we've mainly been working with the grocery retailing and pharmacies. And it's mainly brick and mortar retailing. And the hard thing about brick and mortar retailing is that they generally generate really messy data sets. You have some data points on store level, a lot of data points on consumer level through loyalty programs and such, and a massive number of data points on SKU level or product level. So they typically pretty hard and messy to structure and to work with. So we typically work with a set of different techniques. I come from the statistics side. My home turf is not machine learning. It's old school, boring statistical methods and Bayesian methods. And I work together with some other people in my team who are machine learning specialists and a few who are pure data structuring specialists. So, and that's the way it looks in most of our projects. No single skill set can handle all the different types of data and merge them into one type of analysis. And I just thought I'd share a case that we did. It's actually a mix between different cases, but it looks like one case. In a store, you generally have three big types of costs. You have personnel, and you have inventory, but the biggest one is usually the store itself. So you have to make the most of it. You have to make the most of the square footage or the square meterage. You have to make the store sell as much per square meter as possible. And one store or one chain that is really good at that is IKEA. They have a special strategy for mechanically making people put extra stuff in their baskets and preferably expensive and profitable stuff in their baskets. In grocery retailing and pharmaceutical or at pharmacies, this has not been a focus area, so there's a lot to be done in terms of optimization. And in this case, the business value of this project was about 1 million Swedish crowns per day in lost gross profit due to poorly optimized stores. And it's only, in this case, it was just 700 stores, so it's not it's one of the biggest, but it's not the biggest grocery chain. But 1 million per day buys them a lot of room for playing around with the numbers. So it's a good business to be in if you like data. As I said, it's about 700 stores, and the data point or the data set about the stores is pretty sparse. It's just 700 points. It's really difficult to train a neural network on 700 data points. When it comes to the transaction data, it's about 2 billion lines of data generated every 3 months or so. So there you have a lot of room for playing around with more advanced methods. And at SKU level or a product category level, you also have a very dense data set which you can play around with in different ways. But the problem is that you have to sort of mix these three levels of data into one recommendation or one optimization. And the way we approached this was to be really agnostic about method and to beforehand think of what are the different things we're trying to do. We're trying to reduce noise, we're trying to do cluster stores, we're trying to determine the parameters for space profitability and so on and so on. So we sort of approach them one at a time. And if I'm working with the store as the data set, the choice of methods is pretty limited. I can work with some really simple types of regressions and perhaps Bayesian regressions and some bootstrapping and stuff like that. And when it comes to the other data sets, I'm much more free to try other types of things. But what we did was to think of the different things. What determines a store's sales numbers? It's the size of the store, of course. It's the catchment area, the types of people and the number of people and the wealth of people who live around the store. The competitive environment and that sort of underlying stream of customers going through the door. And you also have the general experience in the store, how satisfied people are in the store, how good they think it is. And we use them to sort of try to clear out as much noise of the data, or to make the data available for other types, for the next step. Because there's a lot of things that are not possible to affect by just shifting around different shelves and different categories in the store on this side. And they are still very influential in determining total sales and total gross profit in a store. And we tried what dimensions can we find that are affecting store sales, and we ended up with a smaller number, and we implemented them in segmentation of the different stores to determine in the next step which data points should be used when calculating space elasticity for every single store. So on this side, we use all kinds of different demographic variables and location and competition. We actually mined Google Maps and mined the walking and driving time between one store and all the competitive stores, and one store and all the customers that had shopped in that store during 1 year. And we looked at what proportion of gross profit comes from people who live X minutes away and so on, and how are that sales or gross profit affected by the presence of competitors. Other types of sales figures, sales patterns as seasonality effects and stuff like that, and also how well they performed in the eyes of the consumers. Was this a good store, an appreciated store by the people shopping there? And this data set is also pretty small. It's about 250,000 interviews. So it's not that small. It's not 700 data points, but it's still too small to merge with the transaction data without losing too much information. And we try to use all the situational variables to guess what sales in a category should be. All the variables except space. So what we basically tried to do was to calculate the residual. If we take all the information we have about the store and in the catchment area and the competition or competitive environment, what should the sales be? And then we looked at, and without using space. And then at that point, we applied more traditional models using standard regressions and trying to explain the difference between actual sales and predicted sales using the number of shelves per category as an independent variable. So what about space elasticity? It's been around since the 60s. What you used to do was look at the gross margin return on space on a category. That's the gross margin generated by the category divided by how many shelves it got, and you try to optimize the store by just increasing shelf space to the point where all categories had the same gross margin return on space, where all were equal. And that works well if you have the same elasticity for all types of products. If some products aren't more impulsive or unplanned than others. And that's not really the case. This is a real case from the UK where we looked at the pharmacy and the average margin per shelf per day was about £500 when it comes to painkillers. And we looked at makeup, which was only £250 per day per shelf. And using the old method, you would just shift shelves around until you had the same pounds per shelf per day. And that's not the case. If we add one more shelf, what will happen? The space elasticity for headache pills or painkillers is much lower than the sensitivity when it comes to makeup. So the incremental gross profit increase is much lower for painkillers. And the reason is simple. People, if they are in pain, they will find those painkillers even if you hide them behind the counter. And that's the way we work when we shop. And the same goes for in the grocery area. The same goes for products like milk. Even if you hide that behind the shelf and place a big sign in front of it, people will find it. It's not like you impulse shop those types of products. But if you hide the candy, there's going to be a really big effect when it comes to sales. So the whole project was actually about determining these space elasticities for different types of stores. And they are very different stores. You might have a 5,000 square meter store in the suburb of Stockholm compared to 65 square meter store in Katterjokk in far north of Sweden with only 65 households around it. So the space elasticity is going to be really different between those stores. You can't really just put all of those stores in the same data set and expect to find reliable results. So what we did was to use the same techniques as we did for analyzing the sales data. We used to cluster the stores. What stores work pretty much the same, because that's the way for us to find variation in the number of shelves without rebuilding the stores. The variation in store build is really low. You typically remodel the store every 7 years or so. So we would have to have a very long data series to find variation per store. So we had to find variation between stores, and we had to make sure that we weren't comparing apples and pears. So we used same types of methods. In this case, it was a random forest, very simple random forest algorithm to classify stores into different classes with similar similar traits and working about the same way. And we iterated this with the results from the regressions as well. So what we did was to look at these stores and draw a line with the help of those. And they contained this set of stores. They were pretty small stores, most of them. So they only had about 15 shelves in this category, or up to 15 shelves. And we used another set of stores to sort of continue the line. And by doing that with slightly overlapping data sets, so we could actually use the same store in several steps here. We ended up with sort of an average elasticity curve for this category. But the average elasticity curve, as I said, it doesn't really work in the same way. So we had to go back and look at store individual elasticities and estimate them in some way. If we look at these 5 stores, this is a real example. 5 stores with very different response patterns. And the reason for the difference is because they are in very different areas. This is, I think this is cheese actually, soft cheese. And this store, the number 3 store, is in this case it says dietary needs, but it's actually cheese, soft cheese. Is in a wealthy area where you buy typically more luxury type soft cheese, and it's much more space elastic than in the other stores, which are in suburban low income areas. So how do we find when we have these elasticity curves, how do we find the optimal solution for each store? We're actually looking at all the elasticity curves simultaneously and try to find out what's the optimal way of allocating space in the store to get the maximum gross profit. And the old way of doing this was you build the store from bottom up. And that works pretty well if you have nice shapes like this, the diminishing return types of curves. Then you can build the store and optimize the store by just adding one section at a time, one shelf at a time. So if the first shelf I should add is a salad shelf, and then another salad shelf, and then another, because the tangent is the steepest there. And at that point, this one, the slope of this one is steeper, so you start adding ketchup or sauces, and at some point you switch back to adding salad and stuff. And if you have a method like this, you will end up with a store with only sauces and ketchup, or sauces and salad. And it doesn't take into account, or it can't really handle curves like this. The problem is that you have 90 categories and you have hundreds or thousands of shelves in some stores. So it gets really messy when you're trying to compare all possible combinations. In just this example, it's a lot of combinations, and it takes a long time to calculate them. So we had to design or actually steal a way of optimizing it. We used some open source algorithms for optimization, and came down to about 15 seconds instead of our first attempt, where the estimation was 1,400 years or something for each calculation. So we are very grateful to the community, perhaps some of you guys. But it's still manual work, and we had to run these things, and it's not really working for the client because they are constantly thinking about rebuilding their stores. So we had to build an online tool for them to input the data about their store. So in this case, a store manager goes in and tells us how many sections they have or how many square meters they have, and out comes the optimal store. And also on the next page, it gives a suggestion, and everyone who's worked with data know that the first suggestion is often pretty stupid or not implementable, because we're sort of building it without constraints or with very few constraints. And they can input some restrictions on the model. The maximum number of shelves for this category should be X, or the minimum number for this type of shelf should be Y. Some of the general restrictions decided by this grocery chain is already implemented, but it could be local stuff as well. So they input the restrictions and get an answer of how much extra money would they earn if they remodel the stores in this way. So in this case, it's 14% raise in gross margin. All right.
Right on time.
Was that one?
Yes, fantastic. Good job.
Thanks.